Swayam Prabha. Digital India. Educated India.
In the last few classes, we have seen how to solve 3-dimensional elasticity problems, taking advantage of geometry and loading and treating them as plane stress, plane strain problems, which are essentially 2-dimensional problems. But some cases we can also depending on whether the problem is involving axisymmetric geometry and loading, we can treat them as essentially 2-dimensional problems, treating them as axisymmetric problems. So, in today's class or in the next 2 classes, we will be discussing about axisymmetric elasticity problems. So, basically as we did in plane stress, plane strain problems, we will be looking at governing differential equation and finite element equations for axisymmetric problems using triangular and quadrilateral elements. So, 3-dimensional elasticity problems involving axisymmetric geometry and loading can be treated as essentially 2-dimensional problems. For axisymmetric problems, the structure, loading and material properties must be symmetric about axis of revolution. For illustration purpose, a typical situation is shown here with z axis as axis of revolution. So, for a 3-dimensional elasticity problem to be modeled as axisymmetric problem, the structure, geometry, loading and material properties must be symmetric about axis of revolution. An axisymmetric stress analysis problem can be formulated in terms of 2 displacement components, one in the radial direction r and the other one is in the axial direction z. So, the displacement component in the radial direction, that is in the r direction, is denoted in the rest of this lecture, it is denoted using u, and the displacement component in the axial direction or in the z direction is denoted with w. This is similar to u and v that we used for denoting the displacements in x and y directions for plane stress, plane strain problems. And because of symmetry, all stress components are independent of theta. The stress and strain components of interest are as follows: sigma r, sigma z, sigma theta, tau r z, and the corresponding strain components are epsilon r, epsilon z, epsilon theta, gamma r z. Assuming small displacements and strains, the strain displacement relations. So, similar to that of plane stress, plane strain problems, we require first to identify what are the non-zero stress components and non-zero strain components, and then we need to also know what is the relationship between strains and displacements, and also how the various stress components are related to various strain components. So, we require all these equations for us to develop the finite element equations based on potential energy functional, similar to what we did for plane stress, plane strain problems. So, assuming small displacements and strains, strains are related to, or displacements are related to strains via these equations, and if you observe these equations, singularity, there is singularity in epsilon theta, that is as r goes to 0, epsilon theta tends to infinity. Numerical simulation, numerical implementation of X symmetric finite elements must take this singularity into consideration. So, these 4 equations gives us relation between strains and displacements, and similar to that what we did for plane stress, plane strain problems, assuming linear elastic material behavior, the strains and stresses or stresses and strains can be related via this equation. Sigma is equal to constitutive matrix denoted with capital C times epsilon, where constitutive matrix is defined like this, which depends on 2 material constants, Young's modulus and Poisson's ratio. And if you compare these equations with corresponding plane stress, plane strain equations, it can be seen that the 2 problems are very similar. Only difference is the primary unknowns of axisymmetric problems are u and w, whereas if you recall, it is u and v in case of plane stress, plane strain problems. For the discussion that we had, if somebody is interested, they can use different notation, but we used u and v for displacement components in x and y directions for plane stress, plane strain problems. So, now to develop finite element equations, we require potential energy functional. Potential energy functional for axisymmetric problems can be written like this, similar to plane stress, plane strain problems, except that potential energy functional now is going to be function of u and w, displacement in the r direction and displacement in the z direction or axial direction. So, potential energy functional is defined like this, u minus w. I guess by this time you can easily understand what u stands for and what w stands for, but for completeness it is given here. U is strain energy, w is work done by the applied forces. So, now we need to see how to calculate this strain energy and work done by the applied forces for axisymmetric problems. So, strain energy, we are dealing with axisymmetric problem. A typical problem is shown in the figure, and u is defined as integral volume integral epsilon transpose sigma, and since the problem is axisymmetric, we can integrate between theta going from minus pi to pi and simplify this as shown in the slide. So, finally, strain energy is given by half area integral of epsilon transpose c times epsilon times 2 pi r. Now, work done by the distributed surface forces, if T r T z are the components of applied forces in r and z directions, then work done by these forces is given by this. Evaluation of this strain energy and work done by the applied forces is very much similar to that of plane stress plane strain problem, except that we need to take care of geometry. That is why you should pay a little bit attention to that. Here we are integrating between theta minus pi to pi, because this is axisymmetric problem, and we can, by doing this, we can actually eliminate theta in the expression for work done by the distributed forces. So, W finally is integral over this, the line along which, or the side along which the traction is applied or distributed force is applied. We need to evaluate the integral that is given in this equation, which is integral displacement in the r direction times traction in the r direction plus displacement in the z direction times traction in the z direction, and entire thing times 2 pi r over, we need to evaluate this over the line or edge over which distributed force is applied. If specified concentrated forces or body forces are present, work done by these forces can be calculated in a similar manner. So, with these definitions, let us develop equations for a triangular element, axisymmetric linear triangular element. A typical triangular element is shown here. The element is actually a circular ring with triangular cross section, and the differential equation involves displacements in the r direction and displacement in the z direction. And similar to that of plane stress plane strain problems, two different trial solutions are required, one for displacement component in the r direction and another for displacement component in the z direction. With 3 nodes, a linear solution for displacement in each direction can be used. This is similar to what we did for plane stress plane strain problems, because we are trying to develop element equations for 3 node triangular element. So, a linear solution for displacement in each direction can be used, because there are 3 nodes. We need to start with a polynomial having 3 coefficients, and since we are dealing with 2 dimensional problem, so the trial solution will be something like u is equal to alpha 1 plus alpha 2 times r plus alpha 3 times z, something like that. So, since there are also, keep in mind, there are 2 unknown displacements at each node. So, the trial solutions for the displacement component in the r direction and displacement component in the z direction looks like this, and both these displacement components are going to be functions of, or they are going to be a function of r and z. Here alphas and betas are unknown solution parameters. The solution, the trial solution, these 2 trial solutions can be expressed in terms of shape functions like this, u and w. This is similar to what we did for plane stress, plane strain problems, and where n1, n2, n3 are the shape functions or linear shape functions for triangular 3 node triangular element, where n1, n2, n3 depends on the geometrical coordinates of the 3 node triangular element. So, once the coordinates of 3 node triangular element are given, then we can easily figure out what is this n1, n2 and n3. So, n1, n2, n3 are defined like this. As you can see, n1 is linear in with linear, or n1, n2, n3 are all three are linear with respect to r and z. f1, f's, b's and c's are some coefficients which are functions of spatial coordinates of triangular element, spatial coordinates of nodes of triangular element. So, if the coordinate information of all three nodes are given, we can easily find what is area of triangle f's and b's, f's, b's and c's, f1, f2, f3, b1, b2, b3, c1, c2, c3. Area of triangle can also be easily computed using the relation that area is half times determinant of matrix consisting of ones in the first row and the coordinates of r in the second row and coordinates of z in the third row of all the three nodes. This formula is already there with you, which we used for calculating area of triangles when we are dealing with plane stress, plane strain problems. So, now so far we have seen how to express the trial solutions for axisymmetric linear triangular element, trial solutions in terms of finite element shape functions. So, now we are ready to actually derive the element stiffness matrix, and these two trial solutions which we just seen, which we have just seen, they can be written together in matrix form as follows, which can be compactly written as psi is equal to n transpose d, where psi is a vector consisting of the displacement components in the r direction and displacement component in the z direction. In order to use potential energy functional, strain energy and work done by the applied forces must be expressed in terms of nodal unknowns or nodal parameters, that is u1, v1, w1, sorry u1, u2, u3, w1, w2, w3. Strain energy in terms of nodal unknowns can be expressed once we know the relationship between strains and displacements, because you know potential energy functional is a function of strain and stress. So, or finally we have seen potential energy or expressed potential energy as a function of strain. So, we need to know what is the relationship between the trial solutions that we just obtained and the strains, so that we can plug in this information into the definition of strain energy. Strain energy in terms of nodal unknowns can be expressed as follows. First, we need to write what is strain vector. Strain vector consists of four components here, and the four components are defined. And now we know u in terms of finite element shape functions of the three nodes and the nodal parameters, and also we know W in terms of 3 finite element shape functions and nodal parameters W1, W2, W3. So, using that information we can further write this vector of strains like what is shown there, and if you carefully see the last part of equation, you can realize that epsilon r is constant over the entire element, because b, all b's are functions of spatial coordinates which are going to be constant for a particular element. So, epsilon r is going to be constant, similarly epsilon z is constant and gamma r z is also constant. Only quantity which is variable is epsilon r, which is function of r as shown in the last part of equation. So, epsilon, this vector or this relation can be compactly written as epsilon is equal to B transpose D, and we need to plug in this information into the strain energy definition, and this is by definition strain energy for axisymmetric problem, and substituting epsilon, epsilon is B transpose D, substituting epsilon is equal to B transpose D, we can further simplify this like the way it is shown there, where K is element stiffness matrix. As I just mentioned, unlike plane stress plane strain case, all terms in B matrix are not constant, and therefore some type of numerical integration is necessary to evaluate stiffness matrix K. One of the simplest integration that you can adopt is one point integration, that is evaluating all the quantities which are functions of x, which are functions of spatial coordinates r and z at the centroid of triangle. Where the coordinates of centroid are given by this r bar and z bar. R bar is nothing but average of all the r coordinates, and z bar is nothing but average of all z coordinates. So, instead of evaluating k at every point, one can evaluate k at the centroid if we use this one point integration formula. That is, k is evaluated by using matrix B at the element centroid or centroid of the element. Or if somebody is interested in evaluating this more accurately, then they can adopt the numerical integration scheme that we already looked at by selecting the points and weights from the table that is already supplied to you. So, now let us look at the other quantity, that is work done by the applied forces, or how to evaluate equivalent nodal load vector. Equivalent nodal loads are obtained from work done by the applied forces. For illustration purpose, consider uniformly distributed forces which are applied along element edges. Let Tr, Tz be the components of applied traction or applied surface force in r and z directions. Then work done by the applied forces is given by this one: traction in the r direction times displacement in the r direction plus traction in the z direction times displacement in the z direction whole thing multiplied by 2 pi r and integrated over the element edge along which this traction is applied. Where Tr, Tz are the components of T applied surface traction in R and Z directions. And so Wt or work done by the applied traction can be compactly written as d transpose Qt, where Qt is the equivalent nodal load vector and Qt is defined like this. So to evaluate Qt we require to know what is n. N is nothing but a matrix consisting of shape functions along the side or element edge over which tractions are specified, or along the side or edge over which we require to, or we are interested in assembling this equivalent nodal load vector. And this integration can be performed in closed form if the specified surface tractions are simple functions of R and Z. Similar to that we discussed earlier, the simplest case is when R and Z are constant or uniform traction is specified along one or more sides of an element. As an illustration, consider uniform pressure applied along side 1 2, that is Tr Tz are constant. Integrations can be performed easily by defining local coordinate system as shown in figure along side 1 2, and along this side the shape function matrix, or to get the shape function matrix we require to know what are the shape functions of n1, n2 and n3, and the shape functions of n1, n2 can easily be written using Lagrange interpolation formula once we define local coordinate system as shown in the figure. Along side 1 2 shape functions n1 n2 are linear functions of S, because along side 1 2 we have only 2 nodes. So n1 n2 are going to be linear functions of local coordinate system S, which is defined along side 1 2, and n3 is going to be 0 along element edge 1 2. So writing the shape functions of n1 n2 using Lagrange interpolation formula, and also with respect to the local coordinate system S defined along side 1 2, we can finally get these two n1 n2, where L12 is length of side 1 2. So with this we can write shape function matrix consisting of n1 n2 n3, which is required for evaluating, or which is required for computing equivalent nodal load vector. So this is the shape function matrix along side 1 2, and then we need to substitute this into the definition of equivalent nodal load vector. And if you see the final part of the equation, we have R. Please note that R can also be interpolated using finite element shape functions. R is that is what isoparametric mapping that we discussed earlier. So R can also be expressed as a function of n1 n2 along side 1 2 before we simplify this equation further. So since R is also a linear function of S along side 1 2, it can be written in terms of shape functions like this. So, now substituting R into the previous equation of Qt, and by integrating each of the terms, here integration of one of the terms is shown, the details of integration of one of the terms is shown. Similarly, other terms can be integrated to get the complete equivalent nodal load vector for uniform load along side 1 2. And once we carry out integration for the other terms also, Qt looks like this for side 1 2. Please note that this is only applicable in the case of uniform load, or Tr Tz are constant along the applied side or edge. And similar expressions for equivalent load can be written if pressure is applied along sides 2 3 and 3 1. If the components of tractions, that is Tr Tz are not constant, then we need to take care of that while doing integration, or we need to use numerical integration scheme to simplify the integrand once Tr Tz becomes complicated. So far we discussed element stiffness matrix and how to assemble equivalent nodal load vector, and rest of the things like assembly and solution procedure are standard, which are similar to that of plane stress plane strain problems that we already discussed, or the earlier problems that we already seen. So, assuming that the solution is obtained, once the nodal displacements are known, the strains and stresses for each element can be obtained similar to that we did for plane stress plane strain problem, but for completeness it is again repeated here. Calculations of strains and stresses, assembly procedure, assembly and solution procedure remains standard. Once the nodal displacements are known, strains and stresses for each element can be obtained, except that there are 4 components of strain and there are 4 components of stresses, and the constitutive matrix is of dimension 4 by 4, and B matrix, strain displacement matrix, is of dimension 4 by 6, except that these equations are similar to that of plane stress plane strain problems. And note that epsilon r, epsilon z, gamma or z are constant over element, but epsilon theta varies with r. This is what I discussed when we are looking at the B matrix, strain displacement matrix for axisymmetric problems. And similarly, the corresponding stresses will have the same behavior. The corresponding stresses have the same behavior, that is sigma r, sigma z, tau r z are going to be constant, whereas sigma theta is going to be function of r, that is it is going to have, it is going to vary with r. So, to illustrate all the things that we discussed so far related to axisymmetric problems, let us take an example and go through all the steps to understand this better. And again in this example tractions are assumed to be uniform for simplicity. So, this is the problem statement: find displacements and stresses in a long thick cylinder under an internal pressure, value is given, internal diameter, outer diameter, outside diameter, and also material property details are given both in FPS units and SI units. Since FPS units, the values given in FPS units are appearing to be round figures, we will be looking at the details of workout in FPS units, but as I repeatedly mentioned earlier, as long as we use consistent units, the procedure wise it is not much different. So, this is the thick cylinder that we are going to solve for displacements and stresses, and as you can easily see it satisfies all the condition that the structure geometry, loading and also material properties are symmetric with respect to the axis of revolution. So, we can take symmetry, asymmetry into advantage, and we can solve this as a 2-dimensional problem. But before we do that, since this is a long thick cylinder, we need to also decide how many or how we are going to model the end effects, or how we are going to model this long cylinder. Since the cylinder is long, the end effects are neglected, can be neglected, and this is how it can be modeled. A horizontal slice of 0.5 inch or 1.27 centimeters height is modeled using 2 triangular elements. So, this is how this thick, long, thick wall cylinder is modeled. Since the length is long, the end effects can be neglected, and the entire cylinder analysis is reduced to solving this model, which consists of 2 triangular elements, and the model is shown with 2 triangular elements, and also the boundary conditions at each of the nodes is shown. Since the pressure is applied from inside, internal pressure is applied, the cylinder is going to expand in the radial direction, and since the cylinder is long, the displacement in the z direction is going to be neglected. So, the boundary conditions at the 4 nodes are as shown, the displacement in the z direction is constrained, whereas each of these nodes is allowed to have displacement component in the radial direction. And element 1 consists of or comprises of nodes 1, 4, 3, and element 2 comprises of nodes 1, 2, 4. At each node there are 2 degrees of freedom, one in the r direction, another one is in the z direction. So, element 1 contribution goes into the rows and columns corresponding to node 1, 4, 3 into the global equation system. Similarly, element 2 contribution goes into 1, 2, 4 or the rows and columns corresponding to nodes 1, 2, 4 in the global equation system. And global equation system is going to be of dimension 8 by 8. So, the contribution from element 1 goes into 1, 5, 6, 7, 8 rows and columns. Element 2 contribution goes into 1, 2, 3, 4, 7, 8 rows and columns of the final global equation system. So, with this understanding, and also one more thing, we need to assemble the equivalent nodal load vector only alongside 3 1 or 1 2, sorry 3 1 or 1 3, because only along that element edge traction is specified, and traction value that is specified with respect to the coordinate system that is defined is acting in the positive direction. So, it is going to be TR and its value is going to be 5000 psi. So, with this understanding, let us get started, and this is constitutive matrix definition, and substituting Young's modulus, Poisson's ratio values that are given for this problem, we get C to be this one. And looking at the geometry of these two triangular elements, we can easily figure out what are the coordinates of all the nodes. So, element 1 comprises of nodes 1, 4, 3, and the corresponding coordinates, geometric coordinates are noted, and all the coefficients are calculated. Once we have this information, one more thing that we require is we need to find what is the area of element 1, which can also be obtained from the nodal coordinate information. And the centroid coordinates and to evaluate epsilon theta we require this quantity. Similarly, these two quantities are required to evaluate epsilon theta or to get the third row of the strain displacement matrix of axisymmetric problem when we are using linear triangular elements. So, B matrix, finally B matrix evaluated at the centroid is given, is obtained like this. So, using this we can easily get the element stiffness matrix. So, this we did because the traction applied is uniform traction, and also if you want more accurate evaluation of the stiffness matrix, as I mentioned earlier, one can use numerical integration scheme that we discussed earlier instead of using one point rule where we evaluated the stiffness matrix only at the centroid. So, now if you see the model, load is applied along the edge 3 1 or 1 3, which actually is a part of element 1. So, applied load vector or equivalent nodal load vector we need to assemble for side 1 3 or 3 1, and to do that we need to note down what are the various traction components TR, TZ, and also length of side 3 1. So, once we have this information we can plug in into the formula that we already derived for uniform traction components, equivalent nodal load vector for 3 node axisymmetric linear triangular element. And we Please note that we do not need to assemble this equivalent nodal load vector for the other edges or sides, because no traction is specified over the rest of the model. Now let us go to element 2 and assemble the element stiffness matrix, noting down the spatial coordinates of all the 3 nodes. We can calculate the coefficients f's, b's and c's, and also we can calculate what is the area of element 2 and the centroid of element 2 with respect to the coordinate system that is defined, and then strain displacement matrix evaluated at centroid of element 2. Once we have this, we can get element stiffness matrix for element 2. So we obtained element stiffness matrix for element 1 and 2. We need to, before we assemble the global equation system, we need to know where the contribution from element 1 goes in, where the contribution from element 2 goes in into the global equation system. That information is noted here for clarity. So element 1 contribution goes into 1, 2, 7, 8, 5, 6 rows and columns, and the locations are given in the matrix. Element 2 contribution goes into 1, 2, 3, 4, 7, 8 rows and columns, and the corresponding global locations are also given in the matrix. So with this information we can easily assemble the final global equation system. Or if somebody is smart enough, they can directly write the reduced equation system, because W1, W2, W3, W4 are all 0. We can eliminate those rows and columns and write the reduced equation system directly. So this is full complete global equation, and the boundary conditions are, essential boundary conditions are W1 is equal to 0, W2 is equal to 0, W3 and W4 are 0. So eliminating the rows and columns corresponding to these degrees of freedom, that is W1 to W4, we get the reduced equation system, which we can solve for U1 to U4 radial displacement components at all the 4 nodes. So once we have this nodal solution, we can calculate, we can do post processing like calculating stresses and strains. Strains and stresses at element centroid can be computed using the element B bar matrix that we already have, because we evaluated strain displacement matrix at the element centroid. But if somebody is interested, at some other point new B matrix needs to be evaluated first before we calculate stresses and strains. So for illustration purpose, calculations of stresses and strains at the element centroid are shown here. So strain at the element centroid is given by B bar transpose times D, and stress at element centroid is given by sigma bar is equal to C times epsilon bar. So for element 1 strain is given by this, and using the, because for element 1 and element 2 centroid is different, we need to calculate this separately for element 1 and element 2, and strain, once we know the strain for element 1 we can calculate stress for element 1, all the stress components for element 1. Similar exercise we can repeat for element 2. and also we can calculate stresses for element 2. So, in this lecture we have seen the governing differential equation for axisymmetric problems and also finite element equations for 3 node linear triangular element. In the next class we will see quadrilateral element for solving axisymmetric problems.